All right, so here we're going to continue on this idea of spanning sets. And we're going to introduce a very particular spanning set called a basis. Right now, a couple things here. Basis, plural. All right, bases. This is singular, referring to one basis of a vector space. All right, so let's define what a basis is. All right, so definition, basis. P. Right? So this says that a subset of V is a basis for V. A basis of V if two conditions need to be met. S is linearly independent and S spans V. Okay. All right. Now here, spanning just tells us that there's enough vectors in there to build V through linear combinations. All right. And linear independence ensures that there's no redundancy. Right. So I get a unique representation, right, which is helpful so that we have one way to represent a vector relative to that basis instead of having infinite number of ways to do that. Now there have theorems before that have been producing bases all along, right? But we just didn't have we just haven't introduced the vocabulary yet. So we've done something like this previously in the course. Right now we do have some standard, so they are like standard bases for some of our vector spaces that we work with often. So here, a standard basis. Now first, let's take a look at our Euclidean M space. So here, the standard bases for the Euclidean M space are these vectors E1, E2, all the way e to the m. All right, and these are E1 is the vector where 1 in the first position, everywhere else is 0. Right, since we're dealing with e to the m, this is the mth position. All right, E2 here, that looks like this, etc. Right, till we get to e to the m. That is looks like that. Okay, all right. Okay. So that is our standard bases. Again, if we, particular example for R3, right, we have three vectors, three vectors, 1, 0, 0, E2, 0, 1, 0, E3, 0, 0, 1. All right. Sometimes in physics or in the multivariate calculus, we call these I, J, K. All right. Our standard vectors here, we use the notation E1, E2, E3. Right. And we know they're linearly independent, right? Because if we set these up as our columns for our matrix, we get I3. And in general, for mth Euclidean space, we would get I sub n. Okay, so we know, right, it is the identity matrix, so they are linearly independent, and I can write any vector in R3 with a combination of these, we could see. All right, now for M, it's a similar concept, matrices of size M rows and columns, right? The standard basis would be the matrices where 1 in one position and then 0 everywhere else, whatever that may look like. right? And then just moving on here, 0, 1, zeros everywhere else, zeros, etc., right? Till we get to zeros everywhere else, 1 here. All right, and let's take a look at, in particular, just to put a specific example, 2 by 2, the bases here would be 1, oops, 0, 1, 0, 0, 0, 0, 1. All right, okay. And then, so we've worked with polynomials is the next one, right? So we've stuck with column vectors, bases, and polynomials was also an abstract vector space that we looked for. Now, in general, P of n, the standard basis is going to be the set S 1 x squared to x to the n. Excuse me. Okay. All right, and then here for P of 4, for example, what that would look like would be 1 x squared, x cubed, x4. Okay. All right. Okay. So here we can show that they span the underlying vector space, right? Rather easily. These basis ones, they cut a lot of the work in the sense that of how we were showing whether a set is a spanning set or not, right? The standard ones make the operations much more straightforward, right? And in the next section, when we introduce the concept of dimension, right, then we'll even simplify our calculations even further, and we'll look for one particular property of these sets here. But one thing to keep in mind is that a basis does not have to look standard, right? So what I mean by that is, well, let's take a look. And so let's say, and this example here, and let S be equal to the set 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, and 1, 1, 1, 0. Okay, so it looks like this. And the question I want to ask is S a basis for M 2 by 2. All right, so for all matrices, row 2, column 2. All right. Okay, so in order for it to be a basis, two things need to happen, right? They need to span the vector space, in this case M to 2, and they need to be linearly independent. All right, so let's take a look. Let's answer the question of, does it span 2, 2? And then we'll answer the second part, the linear independence part next. All right, now we start by, let's set up our linear combination. Zero, 1, 1, 0. It's alpha 3. 0, 0, 1, 1. And then lastly, alpha 4. 1, 1, 1, 0, And can I write this for any A, B, C, D, right? Any constants A, B, C, and D. So any 2x2 matrix. All right, so here through through our scalar multiplication and scalar addition, right, the standard operations that I defined previously, we get alpha 1 plus alpha 4, alpha 1 plus alpha 2 plus alpha 4, alpha 2 plus alpha 3 plus alpha 4, and we get alpha 3. That equal to A, B, C, D. All right, and again, right, it boils down to answering is setting up a linear system and determining if the linear system is consistent. Okay, so here again, individually, alpha 1 plus alpha 4 equals to A. All right, that's what we have here. And then here, alpha 1 plus alpha 2 plus alpha 4 is equal to B. And then alpha 2 plus alpha 3 plus alpha 4, that's equal to C. Alpha 3 equals to A. All right. So what I did here, though, I approached this, I rearranged the rows, again, which I'm allowed to do, right? Row operation, you can swap rows out. This was my first matrix that I started with. And I reduced row echelon form. Okay, and what I got was I wound up with this matrix here. All right, again here, B, C, A, and D, they're just any real numbers, so you just treat them like that. You can do the same operations, you just have, symbolic representation of numbers, right? Being B, C, A, and D. But in the end, I wound up with this augmented matrix. Wound up with B minus C plus D, B minus A, D, and then A minus B plus C minus D. Okay, and this actually gives me, first of all, will it be consistent? And yes, right, I think here, right, if you're having trouble seeing why that's the case, right, what it is going to avoid consistency is if I have a pivot in this last column, but that's not going to happen, right, because I have a 1 here. This sum and difference of A, B, C, and D could be anything, even 0. That's okay, right? Again, the only thing here is that I do not want to pivot here, and I don't get that. So the system is consistent, right, for any values of A, B, C, and D. So yes, S spans 2x2 matrices. Now, is it linearly independent? Well, again, yes, right? If we just look at the vectors and set up the homogeneous system, right, I can just get rid of that augmented part, right? And doing reduced row operations doesn't change this part of my solution, right? And I have 4 pivots, meaning that my vectors, in this case, my vectors are the matrices, they are linearly independent, right? So S spans M to 2, and just based on this reduced row echelon form, right? S is Li, right? Because here in the non and just the coefficient matrix, we get I4. So it is linearly independent. Okay? All right. Now, A basis gives every vector in the space a unique representation. All right, we saw that in the last theorem in the previous video. All right, so now the next thing we're going to do is make the connection, which hopefully you probably see already, between bases and non-singularity. Right, and also how orthonormal bases make coordinates very easy to calculate.